Piezoelectric sensing has a relatively similar name to piezoresistive sensing, but they are rather different things. So let's first start by talking about the piezoelectric effect. So in some materials, mechanical deformation of a structure results in the generation of an electric field across the structure. And this is known as the direct effect of piezoelectricity. In these same materials, bless you, the application of an electric field bless you again, across the structure results in mechanical deformation. Of the structure, and this is the inverse effect. So essentially, there are materials where when we squeeze them, they generate electricity, and transversely, when we apply electricity across them, they mechanically deform, okay? So from a sensing perspective, we're going to be looking mainly at the direct effect, where an application of mechanical deformation yields an electrical signal that we'll find out will be related to the rate of change of deformation. And when we get to the second half of the class, where we're talking about actuation schemes and making devices that do specific things, that's where we're going to use the inverse effect, where the application of an applied electrical signal causes a wanted deformation, right? So there are a couple of key differences between piezoresistivity, which effectively all materials undergo, changing their geometry in some form changes their resistance just based on what the fundamental definition of resistance is. Not all materials experience piezoelectric effect, okay? So that is the one difference. So let's look at this really quickly. So differences between piezoresistivity and piezoelectricity. So number one, not all materials exhibit piezoelectric properties. So only materials that exhibit some form of charge asymmetry in their structure will be piezoelectric. So for example, we might have a crystalline material. And I'm going to attempt to draw something here that hopefully won't be too terribly shitty. So what I am attempting to draw here would be a body-centered cubic crystalline structure. I hope you all are familiar with that term, but if you're not, you'll see what it means here in a moment when I finish drawing this guy. So at present, I effectively have a structure where there is an atom on the corner of each cube face. And now I'm going to attempt to draw one here in the center. So I'm going to try to draw like some diagonal lines that are attempting to depict that this guy is in the center of all of those diagonals, okay? So this particular crystalline structure, which is very common, is not piezoelectric because it is literally symmetrical regardless of which way we rotate the cube, okay? So this is a very common thing. If we wanted to make this piezoelectric, what we would do is a process called poling, okay? And so poling occurs, and I'll write this down in a moment, by aligning all of the dipoles of the material to an external electrical field, and then effectively heating the material up to lock that in. And so the result of poling might look something like this. So once again, I'm going to try to loosely draw something that's body-centered. So we've got our corners of our cube shapes. Like so. And the poling process would actually move that central atom up to say here. Just, that's probably an aggressive shift in the crystalline structure. But the point is that we no longer have that symmetry. So we have the potential for a piezoelectric effect to occur, okay? So on the left-hand side, we have a non-piezoelectric crystal, and on the right-hand side, this one might be piezoelectric. I'm going to write that little bit about poling. So some materials, and typically these are man-made ceramics that we do this to. So after poling, that's with one L, process where all of the materials dipoles are aligned under an external electric field, and then heated beyond the Curie temperature to eliminate grain boundaries. So for what it's worth, and I don't know how much background you guys have in E&M and all of that kind of good stuff, but the Curie temperature is a temperature which is different for different materials. That effectively is the temperature you need to raise a magnetic material to make it no longer magnetic. Effectively, it relaxes all of those latent grain boundaries and reorganizes the structure. So if we apply an E field to this thing to force it to have some particular dipole orientation, and then we heat it up to where all of that latent domains are gone, it'll stick to that particular orientation. And that's how we force a material to be piezoelectric. Okay. So I want to do another little thing here. I don't know why these post-it notes are on the very last page. But essentially, I've got another explanation for what piezoelectric materials might kind of look like. Okay. So think about a structure that might be something like this. So if we had a silicon where silicon is weakly positive in its bonding structure, and then down here we have another silicon atom, and then over here on the left we have an oxygen, and over here on the right we have an oxygen, where oxygen, sorry, that should not be an O minus up there, is weakly negative. If we were to try to compress this structure, doesn't matter if we're trying to compress it vertically or horizontally, or we're stretching it vertically or stretching it horizontally, the center of charge does not change, right? So the center of the positive charge, regardless of how much we extend the top SI up and the bottom SI by the same amount, the center of positive charge will be right here in the middle. The center of negative charge will be right here in the middle. And so it doesn't matter how we deform this configuration, because the center of charge doesn't change, it will never experience a piezoelectric effect. Transversely, we might have something like this. So instead of having a four-sided thing, what if we had a six-sided thing, where here's a silicon, here's an oxygen, here's a silicon, here's an oxygen, here's a silicon, and here's an oxygen. Now when we squeeze the structure, depending on the direction that we squeeze from, we might see the center of charge move up, down, left, right, etc. So this would exhibit piezoelectric properties, okay? So it's all about being able to mechanically manipulate where the center of charge exists in order for the piezoelectric effect to be present in a particular material. So some commonly used piezoelectric materials are crystalline quartz, so SiO2, zinc oxide, Zn capital O, lead zirconate, let me write that better, zirconate titanate. So this would be what's commonly called PZT, and PZT4 and PZT5A are common, and then also polyvinylide fluoride, or PVDF, which is a plastic, is also a commonly used piezoelectric material. For what it's worth, my senior design project involved me and my partner developing a nanostructured PVDF piezoelectric actuator effectively, so that we could apply an electrical signal to it at a high frequency and use it to generate ultrasonic waves for testing materials. That was my boring, dumb senior design project, was making my own piezoelectric material effectively. So that was a noise. um, where do you guys, this is just a quick tangent, where do you guys think you might see piezoelectric materials in your everyday lives? Because I practically guarantee every single one of you has one on you right now. What did you? I said watch. What part of the watch? Exactly right. It's also part of your phones and all of that kind of good stuff too. So quartz crystal resonators are a classical example of a piezoelectric material. That's an actuator effectively. We are applying a specific electrical signal in order to cause it to resonate at a specific frequency. But yeah, every single one of us, if we have a watch on us, or excuse me, a digital watch on us, or a cell phone on us, we've got at least one, probably several quartz crystal resonators on our person at this exact moment. Quite possibly in our calculators and all of that kind of good stuff as well, because that's a lot of how processors time what they're doing, is the use of those quartz crystal resonators and all that kind of good stuff too. All right. So let's see, point number 2 in our differences. Piezoelectric materials are self-generating, okay? So what I mean by that specifically, when we looked at piezo resistive sensing, for example, we always had either some sort of bias voltage, typically a DC bias voltage, or some sort of DC bias current, and our output signal was proportional to those input voltages and currents, right? If we went back to our notes, we would always see there was a term of IDC or VDC in the signal that we were looking at. That will not exist for piezoelectric materials, or doesn't have to exist, let me phrase it that way, for piezoelectric materials, because they're capable of generating their own electrical fields effectively. The compression generates a field, which in turn induces a voltage, and all of that, or induces isn't the right word, but causes a voltage. And so we're good from there. So the signal that is output from a piezoelectric material does not require external power supply or anything like that. That being said, it is typically extremely small. Piezoelectric materials do a fantastic job at potentially generating large voltages. So I'm going to call a large voltage on the order of a volt or two, and we can come up with schemes to amplify that voltage by effectively just stacking up piezoelectric crystals and all of that kind of good stuff. But they're pretty garbage at making large currents, okay? So generally speaking, the output of a piezoelectric sensor is going to be fed into some sort of buffer amplifier, so that it can draw current from external power supplies to be used to do things. So if we need anything other than just a strict voltage, we need something else to help us out on the current front, okay? Number 3, piezoelectric, PLEC, there we go. Materials cannot be used to measure DC, or more generally, time invariant quantities. So we'll get to this in the math here in a couple of minutes, but essentially the piezoelectric response is caused by a change in the material's shape. And so we'll generate a signal every time the material changes shape. So if we just squeeze it, and then we hold that squeeze, we've generated effectively an impulse of voltage. And it's not until we decompress that we'll also generate another voltage and so on and so forth. So we have to be constantly deforming the thing in order to generate a continuous signal. Otherwise, all we're going to get is just impulses, okay? So works fantastically with AC deformations and things like that, or vice versa. If we want to create a resonator, we have to apply an AC signal to it in order to cause it to continuously resonate. Or for a DC signal, as soon as we apply it, it's going to see that one initial change, and then that's it. All right, so those are the major differences versus what we've seen previously. So now let's throw some math at this thing, okay? So mathematically, the piezoelectric effect, let me write this out. Is described as follows, okay? So our first one, T, will be equal to ES minus lowercase e, and then I'm going to try to write this as a script e. And I'm going to obviously have to describe what the hell is going on here because I have three different variations of the letter e in this one damn equation. So obviously this is a bit gross, okay? Before I do that though, let's take another look at things. So this is D is epsilon, another E looking thing, capital script E plus lowercase e capital S, okay? So I'm going to make a note out here to the side that says our piezoelectric coefficient, lowercase e, couples the stress strain relationship, which is how T, capital T is related to capital S in this class, to the D/E relationship. And let me actually write this E as the script E, where that capital D is the displacement field vector that you guys hopefully maybe remember from your electromagnetic field theory courses, and the script E is the electric field vector. So displacement field D is equal to epsilon times electric field, hopefully should be familiar to at least all you electrical types in here. But there's also that additional term of piezoelectric coefficient times strain added to that one. And then the stress relationship, T is equal to Young's modulus times strain. Now we have an additional piezoelectric term, E, and then electric field, okay? So that piezoelectricity effectively couples the relationship between electric field and displacement field, stress, and strain. So now let me literally spell it out, where T is stress, capital E is our Young's modulus of elasticity, S is strain, E is the piezoelectric coefficient, while I'm at it, the units on our piezoelectric coefficient is coulombs per meter squared. Our capital script E is electric field, whose units are volts per meter, typically. D is the electric displacement vector. Where this guy has units of coulombs per meter squared. And lastly, I'll tuck it down here, lowercase epsilon is a material's permittivity. And this guy is measured in farads per meter. In some textbooks, these relationships are expressed as S is equal to lowercase s t plus lowercase d script E, and capital D is equal to lowercase d capital T plus epsilon script E. Just as a note, in this case, lowercase d is the piezoelectric coefficient expressed in, goodness, coulombs per Newton, and S, lowercase, is the compliance matrix. And if I'm being honest, I don't know what that means. Okay. So we've got our mathematical relationships. In this class, these are the guys that I'm going to wind up using, but I wanted to make you aware that if you happen to look at it somewhere else, you might see a similar but different relationship, and so I just wanted you to know what that thing was. So piezoelectric materials are by definition anisotropic materials, meaning that the directions absolutely matter. And so the piezoelectric coefficient has a directional dependency. Fortunately for us, the majority of piezoelectric sensors fall into one of two cases, either a longitudinal transducer or a transverse transducer. So I'm going to go ahead and talk about that kind of good stuff here real quick. So in this case, let's talk about longitudinal transducers first. Longitudinal. So I'm going to attempt to draw a picture here. So I'm going to start by drawing my transducer. So I'm going to outline in blue here. So this is my piezoelectric material. Okay. In purple, on the top and bottom, I'm going to put an electrode. Okay. So this is my top electrode. So it will allow me to either put signal on or get signal off of this material. I need something conductive in order to help facilitate that. And for the math that we're about to be doing, we're going to consider the bottom edge of the piezoelectric material to be at a distance of negative h/2 in a particular direction. And the positive edge of the piezoelectric material will be at positive, or excuse me, the top edge will be at positive h/2. So our zero on this particular direction is the midline of our transducer. Okay. So if I were to apply some force, I'm going to call this F3 because this will be my 3 direction and this will be my 1 direction. And these directions are given numbers to go along with the piezoelectric coefficients we're going to see. So that's why I'm not specifically calling one X, Y, or Z or anything like that. I'll have a force F3 here as well. So if we're trying to expand our crystal, we will wind up generating a displacement field D oriented like so. And I'm just going to put a label here, D3. And then we might measure that voltage by connecting some sort of voltmeter across our terminals or our electrodes like so. So this is representing a voltmeter over here on the left that's measuring the output signal. This is not us applying a voltage, which is why I'm not giving it a polarity or anything like that. Okay. So in this particular configuration, we'll see that our electric displacement vector D3 will be equal to epsilon times our field strength in the 3 direction plus our piezoelectric coefficient E33 times S3, our strain in the 3 direction. And I could express this as epsilon field in the 3 direction plus E33 times the partial derivative of U3 with respect to X3. And I'm going to make a note out here to the side because I understand that things are getting utterly ridiculous. Sorry, that should not be a mu, it should just be a U. U3 as a function of X3 is the materials displacement in the 3 direction at a location X3. Okay. So this last term here for strain is just the change in that particular displacement per unit of that direction, which is exactly what strain is supposed to be, right? Strain, we've measured it previously in this class as the fractional change in length over the length of the beam. Same thing here. This is the change in displacement along a particular direction. So nothing different than what we've done. So what we're going to do now is we're going to integrate across our transducer. Okay. So if we integrate from negative h/2 to positive h over 2, which is in R3 direction. We'll have d3 dx3 there. And now we're going to integrate the right-hand side of our expression. So it's going to be from negative h over 2 to positive h over 2 of epsilon electric field vector in the 3 direction dx3 plus integral from negative h over 2 to positive h over 2 of E33, the derivative of U3 with respect to x3 times, and we're integrating with respect to x3. I am not a mathematician, so I can cancel those things out. That's the wonderfulness of being an engineer, is playing fast and loose with math. And so what this effectively gives me is D3 times the total height is equal to epsilon E3H. All of those things are effectively constants, plus E33, and then we'll have, sorry, I keep writing mu instead of u, the displacement at h over 2 minus the displacement at negative h over 2. So this is effectively top deformation, and this guy over here is the bottom deformation. So what would the electric field vector times height be? It is exactly a voltage. That is the voltage that we would measure across the terminals of this thing. Absolutely right. So keeping on going here, we would have, go back to black. D3H is equal to epsilon V, and I'm just going to make a note here that this is epsilon 3H, okay, plus piezoelectric coefficient mu 3 h over 2 minus mu 3 negative h over 2. And then we are going to divide both sides by h and multiply both sides by the plate area. Okay. So that would give me A3 D3 is equal to epsilon A3 over H times voltage plus piezoelectric coefficient A3 over H U3 of H over 2 minus U3 of negative H over 2. And let's talk about this guy a little bit before I go on and manipulate things here. So if we scroll back up and we look at the units for our displacement vector here, coulombs per meter squared. If we multiply D by area, what do we have? So something measured in coulombs. What's something that we measure in coulombs? Charge. So this term is literally charge. So what about just this part right here? we have epsilon times area over a distance, height. What's that? It is not resistance. So if I had a parallel plate capacitor, what's the expression for a parallel plate capacitor? Epsilon A over some distance. So this is a capacitance, and hopefully that should make sense because we know that charge should equal to capacitance times voltage, and we've got some term being multiplied by voltage, and charge is on the left-hand side. So it should not be surprising to anybody that because we have a goddamn parallel plate capacitor here, we have some capacitance, right? There are two plates separated by a medium that happens to be our piezoelectric material, which happens to have dielectric properties. So we have a parallel plate capacitor. Earth-shattering stuff, right? And then lastly, we have this other thing, okay? So what I'm going to do now is I'm just going to take the derivative of both sides of this thing with respect to time, because I know that current is the derivative of charge with respect to time, and this whole damn thing is effectively charge, right? So I is dq by dt, and so that's going to look like C times the derivative of voltage with respect to time plus E33 A3 over H, the derivative with respect to time of mu3 at H over 2. Sorry, let me close that bracket here, minus the derivative with respect to time of mu3 at negative H over 2. And then as one last step here, so going from the time domain into the frequency domain, okay? So let's say that we were going to periodically deform this thing, okay? This gives us I is equal to SCV. So this is just our conventional AC current because we have a capacitor, plus S times E33 A3 over H, U of H over 2 minus U of negative H over 2, where S is just the Laplacian operator because we are in the frequency domain, or we're in the Laplace domain. And so this guy right here represents our motional current due to our deformation. Questions? Went through a bunch of weird math here and then abruptly shifted into the S domain, just so that we can deal with periodic excitation effectively. Yes.
Sorry, one more time, can you go over what IAC and INL this concept of this one?
So IAC is just literally the steady state sinusoidal current flowing through our parallel plate capacitor, right? So just as, let me go several pages forward here. Okay. So for a capacitor, we know that the capacitor current as a function of time is the derivative, or C times the derivative of the capacitor voltage as a function of time when our capacitance is a constant quantity, right? That's our time domain relationship that we've learned in our physics classes and our circuits classes and all of that kind of good stuff. In the frequency domain, where we would have things in terms of j omega, IC of j omega is going to look like j omega c times our phasor voltage V. And actually that I should be capitalized and it's a phasor current, right? So that's how we would look at things in the traditional steady state sinusoidal frequency domain, okay? But we could also instead work in the Laplace domain where S is effectively just the same thing as, I hesitate to say it's just equal to j omega because realistically it's equal to sigma plus j omega, where sigma takes into account that our signal strength may decay over time. And then the j omega part represents how our signal will oscillate as a function of time. And so that same relationship I see as a function of S would effectively just be SCV, which is where that came from. So 3 different ways of describing the same thing, which is just the current flowing through a parallel plate capacitor. Then we've got this motional current thing. And so this is how the piezoelectric effect specifically is going to contribute some overall current to our system. So we have some that's coming about from the fact that we are exciting this thing periodically. And then we have some other coming about from the piezoelectric effect because we are mechanically deforming this thing and it's going to generate voltages and subsequently currents due to that mechanical deformation.
That would split up that electric current.
Right. Yep. So one is because it exhibits capacitance and the other one is because the material happens to be piezoelectric. Yes. Okay, so if the strain experienced is uniform, meaning that our strain in the 3 direction is just, can be expressed as the change in height over the nominal height, or U3 at h over 2 minus U3 at negative h over 2 all over h, because that difference in deformations is our net change in height, then our relationship for our current simplifies slightly to SCV plus S E33 A3 S3. And I am going to make a note here, here at the end, that this is the Laplacian S, because earlier I said that lowercase s was the term for the compliance matrix in a different thing, and I want to be clear about what it is that we're talking about here. So at this point, we're talking about the Laplacian operator S, or that'd be the natural frequency. Anyway. Okay, so we've got a relatively nice compact form for this relationship. That tells us what happens for our current if we were to apply some external voltage and if we were to mechanically deform this thing. Okay. Now let's talk about our transverse configuration. So once again, I'm going to try to draw a picture here. So here's our piezoelectric material. And I think I used purple before, so I'll do it now. We have our top electrode. And down here is our bottom electrode. Defining a quick coordinate system. So 3 is up top, 1 is to the right, just like we did earlier. If I apply a force in the 1 direction, meaning I try to extend this thing, I'm going to wind up with an electric displacement field, once again, oriented vertically. Where this is, goodness, that does not look like a D. D3. I'm going to call the left-hand edge of my piezoelectric material negative L over 2, the right-hand edge capital L over 2, and let's put voltage sense here. So under this particular configuration, let me make sure I've got everything labeled for my shitty picture in my notes. Looks like I do. We would have D3 is equal to epsilon E3 plus E31 S1, which we could express as epsilon E3 plus E31 du1 dx1, where just as a note, u1 as a function of x1 is the materials displacement in the 1 direction at the location x1. Okay. So following a similar derivation that we are going to skip because you guys are already bored to tears with my math bullshit, we would wind up getting I is equal to SCV plus S E31 A3 over L U L over 2 minus U negative L over 2, or SCV plus S E31 A3 S1. I'll make a note here. For uniform strain. I've got somewhere in the ballpark of a page of notes left here, but I actually want to revisit this because when I was reviewing it, I think last week, I feel like I made an error in the math, so we'll stop here and I'll pick up on this just when I double check stuff on Wednesday about effectively making those measurements and having to use amplification in order to get a usable signal out. I just want to make sure that my simplifications that I've made actually bear out. So anyway, all right. So we talked about the brunt of piezoelectric sensing today. We'll talk about schemes for actually measuring currents using these sensors on, at the beginning of class on Wednesday. All right. Have a good rest of your day. For those of you in electrical engineering senior design, see you down the hall in 25 minutes.